like a rough.
There were two ways. One thing is available memory and available.
Like a sphere.
If you need to 10 or 60,
I don't remember. 6 years ago.
the remaining.
So it takes a second for the camera to respond and the content. Yeah.
I have no idea what you're asking.
There we go.
Google.
It oftentimes takes a little bit right whenever it starts up.
I had a friend that had
And the
them.
call will come in a
Then I
second too.
used them.
Calls
And then I got
them.
which I was like, whatever.
I feel like giving him that's what
Or you're doing the first and second.
So we unmuted and Sharon.
So the first class is in that. But that's 51. It matters. I got through it and I won't ever have to teach it. So
I think it's very.
you're also getting your PhD in physics.
It's paralyzed.
Not at all. The concept might be the same, but the way that they were taught.
Они тренируют
One of these are 58 gigabytes.
маленьких
Because I sat in on Andre's solid state,
Ну, тренируйте делать.
and like he was saying stuff, and I was like,
У меня более модели, which are usually faster than the 47.
so mad.
Those are the ones I'm checking.
And
And if you want information specifically, no.
But you have to have an
А у них
intuition of what to do in physics.
That's why they're not remember which one.
чисто для prediction.
Then in that case,
Everyone has
it's
their own
bigger
thing.
list. There was
Здесь
some
вот
stuff
какая-нибудь
like
такая
which
почва,
is
нужно
guy.
реально
That'd be really helpful. We're using
They said that
Нам нужно
do some dash
So you didn't take majors.
and then instead of putting
Like
all
here,
them,
I took majors, and it's 2 credits, so we met
normally
twice a week.
на сам процесс. Are we ready?
I don't know.
Yeah, ready.
Nothing is mandatory if you everyone is having fun.
Oh, before you start, may I just ask? I just noticed actually from previous meeting, I noticed a few new faces, and we probably can introduce the new people. Or maybe if each of you know everyone, right? It's only me who doesn't know you.
Well, yeah.
Or not only me.
Well, I've met him briefly. I know him. I know Dan.
Okay.
I'm Nathan. I'm a master's student in the physics department.
This year, so you are.
I started this year.
Just started. Okay. And I guess David can introduce yourself as well as a new student.
I'm David. I'm a PhD student in chemistry.
I guess that's one.
Should we introduce ourselves for them?
If
Yeah.
if they need it, because it looks like they might know you already. No.
I don't know.
Okay, so introduce yourself.
I'm Levi. I'm in Svetlana's group. I'm starting my 4th year.
I'm Javed, I'm working in Sweden, same group. I'm starting 5th year now.
Of undergraduate?
5th year undergrad.
It's great.
Jen, I'm Dmitry. I have completed my 3rd year in chemistry.
Oh, I believe that. You sound like you know what you're talking about.
Oh, I'm Braden. I'm first year of Masters in Physics.
But you came. You also local NJCU student. You were undergraduate at NJCU before.
I
No?
was an undergraduate in MSU.
Oh, okay.
Mhm.
Which is
Like right across.
just across the river. Okay.
Hi, I'm Ben. I'm an undergraduate in Svetlana's program. So.
Program. Svetlana's program sounds good. I should really have a Svetlana's program.
And you're a senior, right?
Yes, I'm a senior. So.
Should I add where I went to college then?
Sure.
But we kind of know, right? We had this discussion before. You were talking with Erin, I guess. Yeah.
I went to.
He was also from
Yeah.
Wisconsin.
I got my undergrad at Wisconsin Whitewater.
Everyone knows Deanne.
I got my undergraduate at MSUM. And,
You did? Really? I didn't know this.
I didn't know
Wow.
that. I just know.
Honestly, I didn't know. Okay. I thought you did it in Bulgaria, no? You did it here.
Oh,
in
yeah.
MSU. Ah, okay.
I got my high school diploma in Indiana, in the United States too.
Oh, when did you move here?
I
How
moved
many
here-
years you are in
I
the
came
States
here when I
already?
was 11th grade, and I did 12th grade in the United States.
Oh. Okay.
And then I
What? I said we should really introduce ourselves.
Yeah, I'm Fatima. I graduated from Y.Han Physics Department. I'm working in Dr. Kelly's group. I did my PhD from Y.Han Physics Department.
And then when you're going to get your PhD? Are you going to?
Provocative question.
I'm thinking about November-ish.
Oh, really? So
November.
close. Oh, which November, by the way?
That's a very good question. It's not funny. It could turn out to be next month.
Set deadline by date for deadline. 31st. Is it doable? Yes, if you do not specify the month.
31st.
If you do not specify the month.
31st. Okay.
Yeah.
Oh. Maybe someone don't hear.
Hey, I'm Bakhtiar Rasulov, the assistant professor at the Coatings and Polymer Materials Department.
And just since we kind of touching this subject, on Tuesday, usually we have group meetings for Dmitri's group, right? On Tuesday at 4 p.m. But you will have 1 hour meeting by 5, right?
Well, typically it's 2 hours, but once there will be.
Once means next week.
Yes.
September
We'll do
20.
short meeting for 1 hour, and then second hour will be collaborative meeting with several other groups.
Right.
So we have a meeting for actually mainly talking about machine learning, chem informatics, right? So this is dealing with a grant which we have together in collaboration. So you not really need to come if you're not interested, but those who are interested, you are welcome for next Tuesday meeting to the discussion. So there will be the thing. I don't know whether she will bring some students as well. You probably come with your students, right? And
Yeah, at least
your-
1 or 2 students.
Your student will be mainly presenting the information, right?
I'll ask him.
Yeah, so this is announcement for next Tuesday at 5.
So
And-
if everyone brings students, would be enough space?
So,
I guess we
is-
have enough. Don't
Is
worry.
that going to be like a recurring meeting or just a one and done?
Once per month.
So
once
this
per
meeting we
month.
will do once per month.
Would it be possible to shift the 2 meetings?
No.
Because I teach at 5.
No.
So I can never make it.
Dr. Soon cannot.
Okay.
Well,
Not this time, at least.
what
but,
about
the
October?
next
October
time-
30th, we
Next
have
time
it
it's
at
going to be
4.
different. Yeah,
At 4?
it's going to be at 4.
Let's do,
Okay.
Next time it's going to be
But-
at 4.
But 4 to 5 you are available.
But if you
It depends on how fast
Yes.
my lab gets done, but I cannot do it at 5.
Oh, you have one lab before
I
and then one
have 2
after.
and then 5. But
and if you do not present, if you just listen, it's
Oh, it
recorded.
will be recorded as well.
okay.
And just enjoy. Okay, well, thanks for coming and allowing me to speak.
Finally.
Finally. I haven't prepared anything, but I have to. So next Friday, yes, I do have a presentation on UND seminar, and it's just time to organize my thoughts. If you are busy with your own things, you can just open cell phones and laptop and relax and do your things.
And
So-
watch movies.
And watch movies, yes, I'll just try to tell what we are doing at the group.
So you don't want to watch it?
No, tell what we are doing at the group, and organize thoughts and results for the seminar. Basically, there will be first part, just little story what group is doing, and at the end there will be 3 movies. So just 3 slides with 3 movies, which I really want to show, and the rest is just decoration, which
This formulas.
I will try to skip and not to focus on them unless it is really necessary. But total amount of slides in what I put here is like 130.
Guys, we probably spend night here.
No. No?
Because I'm escaping at 5 minutes.
Okay, there are a couple of grants going on. There are a couple of grants pending. There is.
You have to present it as well? Or?
No, I do not.
It's his acknowledgement.
I will not show it there. Well, actually, the meeting next time will be about this organometallic grant, which is collaborative with several groups and led by Professor Rasulev. One of the, I'm not telling about accomplishments at each group that are coming to this meeting, only the one subgroup. And one of the accomplishments were the back cover of this journal. And I will partially cover the science behind this image in the presentation. And since last overview meeting, there were, well, I'm showing it not to brag, but to give credit to the people who contributed here. So Diane did a nice paper recently, published a couple of days ago.
No cover page.
We tried hard, but it's very competitive. Next time. You won't get Journal of Physical Chemistry letters with cover. There is a collaborative with work with Dr. Burkhaus in Cancun, and there are a couple of conference proceedings by Aaron and by Fatima since June, so it's very, very recent things. I also try to cover them partially, and there are things published at the beginning of the year. Okay, so something is being considered. So if you are Fatima or Aaron and you do not see it published, it means it's still under review. There is a paper written by Yulun that just hangs on me for submission for last year. And there are a couple of projects that are either ready in scientific part and go through writing, and there are projects that are either ongoing or high priority to be completed soon. So Braden would be interested that his ideas inspired other people to do things, and maybe one can combine efforts and do things together. Okay, so recently many of you have visited Boston. You know, it's like, I don't know, water stuff at the waterfront. There was a convention center, and many of you have just seated and listened to the presentations on multiple exciton, which is like interesting for Diane, on relaxation, which is what Aaron is doing, like methods which we all need to do, the perovskites, which is material of today and future, and there were dynamics of interface, photocatalysis, no materials, and things related to cheminformatics were sort of presented. And you may recognize your name here in the poster session. So what is interesting that American Chemical Society noticed the symposium and offered to follow up by a book with proceedings. So consult with your advisor, and there will be space to fit in a couple of chapters. If you
Who would like to write a chapter for the book?
if you
How many pages?
No limits. Can be 100, can be 5.
You can publish your dissertation.
It's so some of you may, if you were speaking, you will obtain an invitation either from organizers or from a robot. So like deadline is coming. Deadline is coming up.
And by the way, when's the deadline?
Right now there are negotiations with ACS. They are not gentle. They try to require everything by 31st. of November or whatever, 30th of November, and we are negotiating to extend it for a couple of months because most of the people will be not able to complete things at short notice. So, actual research. There will be 2 chapters. One on reactions, chemical reactions, since some of us are in chemistry department. And second, the dynamics of excited electronic states associated with change of energy, migration of charge in space for photovoltaic and light emitting applications. But first part is reactions. So why we need reactions and what are benefits of them in this audience, although most of us are interested in nanostructures, in excited states. So one of the aspects why we need reaction is fabrication of nanostructures in order to follow the goals of tuning the properties of nanostructures towards high efficiency of photoluminescence quantum yield or high yield of photovoltaic process of charge transfer. One needs to control properties of nanostructures, which can be done by growing them at a certain size and shape and by tailoring their coverage, the ligands on the surface. And this is mostly challenge for chemistry rather than physical aspect of this problem. So there are surface reactions that happen just activated by heat, and one needs to do a lot of dirty work of trying multiple configurations and checking the binding energies and preferable sites for special ligands, finding special sites. And so it is for covering surface nanostructures. Another aspect is how the actual nanostructure is growing in either colloidal or gas phase. So how the small molecules of precursors nucleate together to form a nanostructure. And originally this research was connected to attempts to break molecules on parts. So that it is not connected to what I'm going to show today, but it was forming a basis. So this is projects that are going on in collaboration with Dr. Burkhaus. So surface of so-called wet halide perovskite can be covered by different ligands, and one just directly measures binding energy by practicing thermal desorption. So looking at which temperature the ligand desorbs into vacuum if one heats it. And by assuming mechanisms of co-adsorption and different binding sites, one can find computed energies close to what is observed on experiment. And so by now, what one has completed is adsorption of carbon dioxide, which stops being dioxide on the surface. It finds residual water from the moisture, forms bicarbonate, same like a drinking soda, right? And it adsorbs much higher than carbon dioxide itself. The ongoing research deals with formic acid, and the interest because it's simplest carboxylic group, which is typically used in quantum dot ligand formation. So here it goes, it desorbs at much lower energy, and there are some additional challenges to resolve. So reactions. Reactions can be activated by heat, photoexcitation, or intense photoexcitation. And in order to treat this, one has to take into account that electromagnetic radiation oscillates quick, but if it oscillates quick, then your operators, your Hamiltonians, changing time really quick, which makes your life hard. It's numerically untractable. But if one practices so-called rotating wave approximation, then quickly oscillating terms drop, and Hamiltonian becomes either time independent or very slowly changing. So there is an attempt to combine the standard tools for recurring structure calculation and the handmade inclusion of the light to matter interaction term into Hamiltonian, which makes a system of coupled equations for both electronic and nuclear degrees of freedom. So this slide can be mostly interested for Dean, and maybe he will develop a criticism. So if your electronic system undergoes continuous radiation by light, there are so-called Rabi oscillations of the occupation and also of off-diagonal elements of density matrix. And the amount of flips, of Rabi flips, is proportional to so-called area under the pulse. You integrate the interaction Hamiltonian and convert it in unitless angle. So 2 pi angle means return to original state, pi means flip, what was occupied becomes unoccupied. And if one assumes that instead of CW excitations, there are trains of pulses, then flips of occupations happen only when these pulses do arrive. And the occupation suddenly jumps from occupied to unoccupied. In some sense, this could be interesting for Jabet and for Levi. This is similar to surface hopping, when one assumes that off-diagonal elements do not play any role other than auxiliary abstract thing, and actual occupations are either ones or zeros. So this is the same protocol coming from different consideration. But if one accepts an approximation of replacing continuous pulse by a train, continuous irradiation by train of pulses, then one can assume that electronic states are always either occupied or unoccupied, which is very comfortable for numerical calculations. You do not need fractional occupation, you just have occupations equal 0 or 1. And in this approximation, you just add a protocol, computational protocol that allows jumps of occupation between 0 and 1 in the necessary states, and you run simultaneous coupled system of equations for electronic degrees of freedom and Newtonian mechanics for nuclear degrees of freedom, with understanding that forces do depend on occupations. So originally, and Professor Rasulov left, but it's his credit of converting outcome of the time-dependent excited molecular dynamics into mass spectra, because if there are either fragmentation or association of products, one can convert the outcome of the simulation, the trajectory, into distribution of products at certain masses. So, irrelevant thing. It was just a guinea pig, which has nothing to do with Guinea or with pig. Application of this methodology to fragmentation of metal-organic complexes with one metal antonite in the center and cyclopentadiene on sides, and lowest excitation is from ligand to metal. And upon running such trajectory, the bonds between metal, carbon and hydrogen become less and less stable. So because energy is being pumped by light into this degrees of freedom, And in some sense, it is equivalent to ramping up the temperature linearly. So if one follows the temperature, it grows to about 10,000 Kelvin. And it's enough to break several bonds. And if one watches this movie long enough, it shows formation of several products. Like there will be acetylene, hydrogen molecule, and different metal to carbon intermediates and products. The goal of this project was to excite it to such state that a metal ion will stay alone, and if it doesn't happen, explain why. In some sense, one can interpret it as single metal ion catalyzing the reaction of hydrocarbons. Just justification that if one goes from DFT to LT-reference, the trends of energies of intermediates are not so bad. And here are the mass spectra. This is only justification of the method. So the experimental observations and computed mass spectra. So if we start with heavier fragment, start to crack it with light, it peels off hydrocarbons and becomes lighter, and there are several pixels in the mass spectra. Okay, and now the recent work of Dr. Yulun. So before method was tested for dissociation, for fragmentation and breaking things onto the pieces, and now it is for association. There is an experimental group of Professor Phil Bujak at NDSU. They designed practical ways to synthesize reliable cyclohexasilane molecules which have unique properties. So it is a transparent liquid which converts into solid silicon if you radiate it by light or heat. So why don't we try to see if the photoexcitation can help to polymerization, or if you want to be conservative, to dimerization of these precursors. With understanding that if this reaction goes far enough, finally it will generate silicon nanostructures like quantum dots, thin films, nanorods. And if the natural intuitive expectations are that if we start from small size precursor molecules, they would have spectra in the UV range of, and as soon as association and polymerization goes on, it shifts to the reddish part of the spectrum. So the molecular dynamics, if one scrolls it far enough, may give things, so it's time dependent excited state molecular dynamics, may give some intermediates close to dimerization. But analysis of the intermediates along the molecular dynamics is really complicated because the uncertainty of atomic positions and part of the energy from kinetic motion. So if one compares two nearby time steps, they may have drastically different potential energy, although total energy is the same. So one of the tricks that Dr. Yulun designed was so-called full intermediates, when one takes snapshot at each point of the dynamics and then relaxes it, assuming that in the experimental apparatus the reaction, the jet of precursors goes through focus of laser, and then when they pass further, they have an opportunity to dissipate energy and cool down. And if it is ensemble, one can analyze distribution of possible products. So through this cold intermediate, it shows formation of like, it's not quantum dots, but clusters with multiple 3 and even 4 coordinated silicons, while in the original precursor they all are 2 coordinated. Like each silicon has only 2 silicon neighbors, right? Well, there are some additional technical details. I don't know if they are super interesting, but depending on the original orientation of the precursors, the pathway of the barriers or reaction steps is different. So, but this is too high of energy to overcome from through heating. Therefore, one needs at least one or sometimes more than one optical quantum to overcome these barriers. So it's energies of intermediates as long as reaction goes. But the final products, independent of original orientation, come to similar configurations. Well, we all do like exploring density of states. Originally, density of states gives gap over 4 eV, and as we go to this association, it shrinks. Well, in calculation with DFT, which is a little substandard to predict gaps, it shrinks too much. It gives just qualitative trend of larger cluster, shorter gap. In fact, the experimental observation of the first steps of the reaction, and it goes through minutes rather than hundreds of femtoseconds because they have lower intensity, and in simulation we exaggerate the intensity. It shifts to red part much more conservative, not as in calculations, but the trend is there. So the longer reaction goes, the redder becomes the spectrum. If one would continue this problem, one would probably try to look at the intermediates and process them with higher level methods, at least TDFT or maybe some multi-reference or excitronic methods. So this is only a trend, how the gap is changing, and there are additional tools that we will discuss later, how to convert electronic structure along the molecular dynamics into photoluminescent spectrum. Basically, it would correlate with just oscillator strengths at the lowest transition, with some additional factor for the width. And there is an interesting observation that as long as we change wavelengths of initial excitation or original orientation of the precursors, one can observe both fragmentation onto smaller, like Sylvain gas with only single silicon, or polymerization with heavier fragments. But by changing wavelengths of excitation, one can control and enhance one pathway against another one. Okay, done with reactions. Now a little bit more fun stuff for electrodynamics in nanostructures. So since we were already talking with silicon nanostructures, they can be, any nanostructures can be prepared with different dimensionality, like quantum dots, nano rods, nanowires, thin films, and bulk is not nano. In nanostructures, the everything except quantum dots, there is an additional degree of freedom for electrons. They have translational motion, right? And it means that electronic structure needs to be recomputed at each value corresponding to this translational motion, different average value of momentum. So this makes the situation a little more complicated, and additional tricks need to be added to a standard approach for electron dynamics. So as soon as momentum gets higher, the energy of the orbital of the same symmetry gets also increases. So same like in classical mechanics, just kinetic energy, velocity squared, momentum squared. And we are looking for dynamics of how the photo-excited electron will migrate in energy. So this challenge is by today partially addressed by Fatima, who is sitting on the last row, and I'm not going to show technical details, just a brief overview. And my goal is to just show one movie. The rest of information is just to prepare. Well, totally there are, I lied you, 4 movies. I already showed one, and I want to show other 4. So there are nanowires which are infinitely long sticks of silicon, and because of the crystalline structure, they can be grown in different crystallographic directions. So silicon has same structure as diamond, and in diamond you have this tetrahedral, and you can align with one of these tetrahedral things or put it to like 45 degrees to them or other degrees. And if you continue it infinitely long of one of the directions, electronic structures will be different, and it can be made on experiment. So one of the features in this dependence of electronic energy of momentum is that it is not always growing as you increase momentum. In some exotic, or maybe not always exotic, in some materials you can increase momentum and energy will decrease. And this trend for increasing and decreasing energy as function of momentum can be different for occupied and unoccupied orbitals, for electrons and holes. So for intuitive, normal materials, the minimal energy will correspond to 0 momentum, and it will be maximum for holes and minimum for electrons. This is standard and intuitive, and it's called Dirac gap in conducting. But sometimes the lowest gap happens between occupied at one value of momentum and unoccupied of another value of momentum, which needs special treatment. So the challenge in this work was to take into account transitions which either conserve momentum or violate conservation of momentum. Violate not in a sense that violate rule of momentum conservation, but momentum departs from electronic subsystem and is being transferred to a subsystem of nuclear degrees of freedom. So electron stops, it was moving, it stopped moving, like in Beware, and then a nuclei or set of nuclei started moving. And we are focusing only on the electronic degree of freedom, therefore we allow transitions with local violation of momentum conservation. Yes?
I have one confusion in this, in my confusion is
yes,
not
yes,
about this. So when it's changing the momentum, is it like it's changing the momentum but electron in the same state and then is going to certain momentum and then is relaxed down? Is it same thing like that, or during the changing the momentum is also changing the state of the electrons?
We do allow both, and we see that simultaneous change of band and momentum is non-zero, but it is a numerical observation. Intuitively, one would expect that one can decompose any transitions on either vertical transitions and then change of momentum along one. Yes, it was our original expectation, but numerical results show opposite, that it can go on a diagonal. And here is movie number 2 that I would like to show. So run it several times.
Actually,
So,
Yes.
but these results, when you say that this is what your calculations show, I think it was based on some of the talks which we discussed during summer, and there was a question about normalization.
Yes.
Is it based on this already, or at least checking these normalization issues, or it just?
No. Normalization is additional issue which will affect the reported rates of overall cooling of a hot carrier. Normalization doesn't affect the individual rates. The normalization question is how does one construct the matrix of individual rates in order to consider the complete dynamics. So calculation of individual transition rates are independent of discussion of normalization. And they seem to, right now we do not see any problems with them. Normalization, yes, it needs to be, it is not added yet, and it is next thing to do. But even with all possible improvements, the individual rates will not be changed. They are what they are, and there is no reason to change them. So what we see here, this is diagram showing distribution of charge density as function of energy and momentum at different time steps, points of time. It's only for unoccupied orbitals, for electrons where holes are skipped. So just systematically, one can assume different initial state. So here it is supposed to be some non-zero momentum, some non-zero energy above the volume. And then these yellowish circles show how along the time there is a superimposed distribution of charge density at different energies and different values of momentum. The red line shows expectation value of both energy and momentum at given point of time, so it goes along this line. And it is interesting, but quite expected, that for this indirect gap nanowire, the final state, final value of momentum will be non-zero, not at gamma point, but somewhere in between. Another interesting observation is that it will be not purely one state, but it will be superposition of several states with different values of momentum. So since their difference is not very large compared to thermal energy, it will be simultaneous coexistence of several values of momentum in the LUMO orbital. Why there are 3 points? Because it is numerically demanding and expensive calculation. In ideal world, one would repeat it with finer grid of values of momentum to have more continuous rather than discrete distribution.
So what's your delta in momentum? Is it 0.1?
It's 0.16 or something like this. So it's
the same as those
yes.
points.
But
not
it
the
is,
same data.
It is 0.5 divided by 4. 0.125 about.
So can I say that like final points and initial point is a realistic points we can compare in the real scenario, but this continuous pathway is maybe not the real way. Is there something like that?
Well, real things are only what is measured in
I mean,
experiment.
in practical sense, can it cross this like continuous path in the subgap, or it should be vertical in that side, in the subgap?
Well, even if there are no states in between, if you make superposition of states before and after, average expectation value can be in between. This is an argument why some people like surface hopping against Ehrenfest, because Ehrenfest has average value in between actual states. But here it is expectation value between the eigenvalues is normal thing. It just represents superposition. Right? Yes?
This could be a really stupid question, but
Well,
so,
I can answer with very stupid answer.
so as the electron goes down, right? Should the energies of the look of the molecular orbital as a function of momentum change shape in response to the electron movement?
It's an excellent question. Let's analyze it together. So the orbitals really look very similar. So this is Luma plus 1, right? And it just takes too much energy to draw orbitals for other bands. So here this diagram on the left illustrates only two lowest band in this dynamics. And definitely we see some change as we, with one band, we go along. But it is really hard task to identify what is being changed. So silicon has a diamond-like structure. So it's expected to be like sp3 for occupied. For unoccupied, it is some superposition of p orbitals, right? P orbitals meaning there will be no density on the atom itself. It will be nearby, which you can kind of see here, right? So atoms are not covered by this yellow density. But what happens further is too much for human brain. If you come up with ideas, please communicate them before next Friday. So one can see that maybe there will be nodes and lobes along the axis, or those are continuous. Maybe some of the orbitals have more density on actual bond, like bonding orbitals, and some have, here it is more anti-bonding character, but it really needs chemical intuition. How this superposition of p orbitals come up with more complicated envelope function, or what is going on when we change the momentum. Typically, higher the momentum, larger number of the fringes. And here there is 0 point, so there is at least one fringe. But it is very hand-wavy. Systematic analysis of orbitals is a big challenge.
Can you get that analysis from Procar file? Like positive dose file?
Procar will show that they all are on silicon p orbitals. It may show distribution, how they're composed on px, py, pz. So it could be insufficient. Yes?
Wouldn't you just subtract or take a weighted average of these cube files, and then as it progresses between them would be the average, and then you can make the big.
That's a great idea. And main expert who is doing this calculation may try to do it. And there was a little technical challenge how to label orbitals, because now they are labeled by two quantum numbers, index of orbital and value of momentum. And one wants, it is much more comfortable to have just one index. And one can combine them. Like for Luma and different values of momentum, we progress number of states that we do linearly, and then we start over in the next band. We'll continue the 5, 6, 7, 8, right? So number of actual states, or how to say, bands with special value of momentum is bigger than the number of orbitals, right? Okay. Perovskites are cool. I would love to have some results on the perovskite nanowires, but things take time. There are several challenges in basic questions about perovskites, and but most of them are inspired by their applications for either photovoltaic or light emitting. And for light emitting, several of you are involved in the quantum dot business, you know that depending on the quality of the surface passivation, the lowest transition can be bright or dark. So there is a question how to passivate surface so that the quantum yield of photoluminescence will be larger. Best light emitters are quantum dots, but in simulation one needs to have surface termination from each side, and sometimes it is easier to study surface effects just on thin films. So this is work of Daniel Ramirez, and he is trying to passivate the surface of lead bromide, cesium lead bromide perovskite by combination of anions and cations according to standard procedures in literature from the Switzerland group of Maxim Kovalenko. So when one combines both anions and cations, in average layer of ligand is neutral, has band gap higher than natural band gap of perovskite, and prevents surface from having trap states. There is a question to which literature doesn't give an answer. The perovskite lattice can be considered as sub-layers rich in cesium, this cyan elements with bromine, and then lead, which is kind of goldish with bromine. So cyan or lead, which surface one can absorb same ligands on both surfaces, but which one is more preferential to have better light emitter? And in order to address this question, Daniel did try to put same distribution of ligands on either cesium-rich surface or, well, we do not see it here, lead-rich surface. And then there is a, by now, pretty standard procedures to run electron dynamics and follow charge distribution as function of position. So at these diagrams, the x-axis is time and y-axis is position z across the slab. So at time 0, in both cases, the excitation is distributed in space between ligands, approximately in the space in between. Well, not always, but it was an attempt. And as time passes by, the question is whether both electrons and holes will stay in the slab and keep this lowest excitation emittive, or either electron or hole will migrate to the layer of ligands and quench the luminescence, make the state dark. So for the cesium-rich layer, calculations of Daniel show that it is either being excited all the way to state where hole stays on the ligand, or even if one starts with equally distributed inside, as time passes by, one of the lowest state would be a trap state for a hole. So bluish orange correspond to electron, bluish correspond to hole, and this greenish to neutral equilibrium distribution. So according to results by Daniel, the cesium-rich surface is bad for photo emission.
Is this structure symmetric in z directions?
In z direction, it is a set of periodic slabs separated by vacuum.
But
and in x and y, it is periodic. It is a thin film, infinite thin film.
I mean, is it symmetric in the z directions, like lower half is upper half?
Identical, yes.
Identical.
Identical, yes. So
you still
you see blue cyan at the top, cyan at the bottom, right?
But then, isn't it charged?
What do you mean charged?
The charge balances.
Each system is neutral.
Overall system is neutral.
Overall system is neutral. There is a local redistribution of charge, but overall system is neutral. Number of anions and number of cations are equal.
So in this case,
So it's not enrichment, it's just different cut. Like you still
It's
have,
different cut,
you
yes.
still have the same number of everything.
Same number of
Just
everything.
cut different.
So, good question, and Daniel, where are you? If you're watching this record, put the answer to Levi's question into the paper. So, each of the sub-layers, either cesium-rich or lead-rich, is stoichiometric. So, bromine is 1 minus, cesium 1 plus. So there are cesium 4, bromine 4. So it's neutral. The next layer is lead 2 plus. Lead 2 plus is lead 2, bromine 4. So it is also
So it has how many on the first? So it's
on the first there are 4 cesium and 4 bromine.
So
On
that
the next are
would be
2 leads. Yes, 2 leads and 4 bromines.
that would be 6. So, but
Lead is 2 plus, bromine is 1 minus.
yes, but how many atoms are in that layer?
2.
8 or 6?
6.
So then, isn't this somewhat like rock salt?
No, it's cubic. It's 3 component.
Oh yeah,
It's
not-
3
yeah, yeah,
component.
Yeah. Okay.
The so the lead is octahedrally coordinated to bromines, and cesium ions are not coordinated to anything. They are floating in between. They're not literally coordinated. They're just filling the cavity. So if one repeats these calculations for the lead-rich surface, there is a slight migration of the partial migration of the negative charge to the surface. But in average, it is much more homogeneous and it promises to be a better light emitter. So it's main result of the work by.
So I'm just wondering, in the first case, is the hole localized in the top hub or in the bottom surface? Is that same thing, or is that have any significance?
No.
Because
It's,
the system is identical in this case. I mean, in symmetry in this case.
even we need to bring here Daniel for exact initial state for this excitation. But it is expected that there will be a progression of the degenerate states of this localized of holes, top and bottom.
Okay.
But in numerical treatment, nothing stays degenerate. Degeneracy is always broken. A spontaneous break of symmetry by some little corruption of geometry. So there is a lift of degeneracy, and definitely one will be a little lower and another a little higher. Therefore, we do not see equal splitting on the.
So did he also check if the parent system is more stable in one configuration versus the
Which system?
remove the ligands and check if the bulk material is the reason for this, or if it's also like did he check if it's the bulk material properties that are doing this, or the ligand?
It would be really great if he has done it,
So,
but even if he did, he didn't report it to me.
okay, so this might be
Natural,
coming from-
natural supplement to these results. Yes.
Okay, but this could be coming from the fact that you cut it in different ways, and that could.
Well,
or no.
not from Daniel, but from literature. The surface without termination will be good absorber but bad emitter.
But I guess what I'm asking is, does the surface in and of itself change the properties? So if you compare not with the ligand compared to no ligand, I'm saying if you compare the two ligands, like two surfaces that are cut, without ligand to themselves, would this property also be shown? Or is it intrinsic to the ligand?
I understand your question. Intuitively, both would be bad. Without ligands, no matter which cut, both will be dark.
Okay.
It's quite of surprising. It was expected that any surface covered by ligands will be bright. But it's interesting that not any. One of the... Okay, we are not done with 2 hours. So one of the applications of perovskites is photovoltaics. When you photoexcite it, and then there is a photoinduced charge transfer, and then it goes to leads. So the question is how to attach electron acceptor and hole acceptor to this perovskite and pull photogenerated charges out of this material. So Landon Johnson is exploring how to pull electrons out of perovskite, and he is trying to address specific challenge. Generally, for photovoltaic cell, one has this perovskite material, light absorber, then electron transfer medium, hole transfer medium, and then contacts. So he's focusing only on this interface and looking onto structure-to property relation, how the material of choice as electron acceptor is titanium dioxide. But there is a long way of possible variation of how one can construct interface. Will it be transfers through space, transfers through chemical bond? What will be how they will be connected or disconnected? Of course, one cannot check everything, but practical thing would be to put either carboxylic or hydroxylic group on the interface. And before calculations are started, there are at least 2 possible expectations to check by computation. One is that the perovskite and titanium dioxide will form type 1 heterostructure, or either here or there it will be neutral excitation, or the alignment of bands will be different for electrons and holes, thus promoting formation of charge transfer. So, if you were here on several group meetings, probably you have seen how Landon was presenting his structures. So, the structure here is perovskite, and here's the cluster of titanium dioxide in two different orientations and 2 different ways to set up connection to the perovskite site. So first, how the cluster is constructed and why it is cluster rather than large periodic bulk of titanium dioxide. If you know that this would be interesting and pleasant to hear for Jabet. So if you are trying to build an interface of 2 semiconductors of different lattice periods, and you are doing not quantum dot as you do, but you try to do periodic, infinite periodic structure, the lattice mismatch would accumulate as you grow cell, and it will create strain. And strain means elongation and contraction of bonds, which will screw up the energy of an electronic interface. So this is interesting effect, but it's a lot of work, and it's not clear that it is necessary right here. But if you do 2 quantum dots or quantum dot with periodic structure, this effect is gone. So it is just much more comfortable to, as you know, to work with dots rather than periodic structures with mismatching lattice periods. Same is in the work by DM. In your recent publication, you have infinite with periodic nanotube and finite size quantum dot. So your periodic size is not suffering of lattice mismatch. If you try to put nanotube on the infinitely periodic slab of silicon, it will be big strain and it will be major complication.
Who's making these figures?
Landon?
Oh, looks really nice.
Well, he's learning and progressing. So, but if we go to the idea of using cluster instead of periodic, instead of infinitely large slab, then the question is stoichiometry. So one titanium per 2 oxygens. But if you cut the surface, here it's like 6 titanium and 6 oxygen. It's non-stoichiometric. So one needs either to put oxygens aside, and one needs to avoid trap states, same as we always do for quantum dots. So one needs to design ligands that will allow this cluster to mimic the gap of the periodic bulk or the cluster. This is not purely creative credit of Landon. The idea of which ligands are to use are known from experiment. In fact, the small clusters of titanium dioxide are possible to crystallize in the super array of these quantum dots, and positions of each atom can be extracted by X-ray diffraction. So there are research groups who do it, and here credit goes to John Fogel, who looked through the literature and suggested which coordinates to use. So there are well-defined structures of bright titanium dioxide clusters. And there are also dual ligands, isopropanol and first is formic, second is acetic, right? So, and then if one wants to facilitate charge transfer, these ligands they will be like isolated. They will not allow charge transfer. So therefore, in order to facilitate charge transfer, one can pull off a ligand, but for chemical stoichiometry, put simplest possible ligand like hydroxyl, and then smash the surface into perovskite. This is kind of too many technical details, but it is a good mimic of what is going on in experiment. And opposite consideration, if we didn't tear legs of a bug and didn't smash it into the surface. It's just almost same electronic structure, but facing by this semi-dielectric carbon-carbon stuff towards perovskite.
Question.
Yes, please.
So are the carbons all the same? You just remove some of them to put.
So we do not remove the acetic. There are 6. So stoichiometry is 6 titanium, 6 oxygen,
Okay, so
6 acetic, and 6 isopropanol.
Okay, so you just remove
3 isopropanols. 3 isopropanols and replace them by.
And the rest of the structure is the same.
Otherwise, it is the same. Okay. Oh, no. Vortex. I probably by mistake pushed the end button, and now I better find the spot. Okay. So again, there is a comparison of 2 structures. One with hydroxyl, another with acetic. Part of the cluster facing the perovskite. So Landon did practice this almost standard protocols for non-adiabatic dynamics facilitated by nuclear motion, and computed the dynamics of charge distribution on the color as function of position, y-axis, and time, x-axis. So in case of the acetic acid, original excitation always goes to perovskite. So you see this alternating blue and orange, which means the initial excitation stays on on perovskite. Orange means lead 5s orbital, and blue would be bromine, whatever, p6p, whatever is available there. And as time passes by, both electron and hole do migrate to titanium dioxide. So there is no charge transfer. Well, there is one very short transient charge transfer. By the way, it is similar to what Dan computed for your recent work. So transient short period charge transfer. And then later, lowest excitation, both blue hole and orange electrons stay on the acceptor. So final state is neutral. But if we allow this structural change by replacing isopropanol with hydroxyl, we start on both electron and hole originally on titanium dioxide, and then hole stays on the slab on titanium dioxide, but electron does transfer to the hole stays on perovskite slab, and electron jumps to titanium dioxide. So just a little chemical tweaking of the linker makes drastic change in the quality. Yes?
Is the color scheme is same in the both figure?
No. No.
That's but in the bar by the picture image, their color scheme is.
This color scheme is a little better. Ideally, the green color in the middle of the rainbow progression should correspond to neutral. But
in the bar, the color bar is showing the same bar. Yeah.
No, but that's from like -7 to like 20.
And that one?
That one we can't really see, but it's much smaller.
This one is to be correct.
But I have a question. So it appears from the system to your dynamics that the whole, I think, the yellow goes to the hydroxide groups on the titanium dioxide quantum dot, not to the quantum dot itself.
No, if we align, it would be more like this titanium and oxygen. So there is no substantial density on hydroxide. It's more like mediator. See, those are layers of perovskite, and this would match more to this titanium and oxygens.
So is there a reason why they stayed on the near atoms instead of going throughout the entire?
Yes. System is polarized, and electron and hole attract each other.
They're bound in that case still?
Well, in this methodology, we do not have excitons. We do not compute how they are bound, but they should be. Good eye. And now it's time for the. What's going on? Oh, let me answer your question with a movie. Movie number 3 that I always wanted to show. So it is a favorable configuration.
Is it also from London?
He contributed substantially. So you see, originally it was yellow and
I didn't see the movie. Where is the movie?
It's
no colors develop.
It's very slow. See, it develops here.
I don't.
You don't see the yellow?
It's growing.
Yeah, it's growing colors.
The movie is not.
Be patient.
That's it?
That's it. It's not very dynamic, but it's of extremely high scientific value.
That's indicating the
makes me feel better.
If you are not, if we are not so patient, we can just do it like.
Oh, this is better. At least something happening.
It's the log of time.
Yeah,
the
time is
movie
log
in
in
linear
log
time, right?
It's not linear time.
The movie is in log time too?
Yes. So
probably take out several steps. You should go with the larger steps.
no, then it is very choppy. So See, originally there is very small orange density on titanium. Titanium is these blue atoms.
What is in the bracket T1 and T7?
So there is on bromine and lead. And then, Levi, here is your hydroxide. So there is both electron and hole in the hydroxide. And then it substantially grows the yellow electron density on titanium 3D orbitals. See this like 4-petal structure.
So then why is it so intense on that titanium compared to the others?
Because we have...
and again, hole is on titanium, right?
No, wait.
Electron.
Wait, electron, yes. Don't you know that electrons are yellow?
So what is that in the yellow circle?
Huh?
What is this atom in the yellow circle?
Well, this is, well, color codes do not correspond in this image, but these blue atoms are titanium. This is not the whole structure, but it's only one slice across the middle of the structure. Otherwise, if one adds together and integrate it, it becomes uncomprehensive. And the relative density on titanium is much higher than the relative density, let's say, on bromines, because there are a couple of dozen of bromines and only like 6 titanium. So if we equally distribute equal amount of charge on bromines and titanium, relative amount on titanium will be higher, right?
Your titanium is just in one space and bromines are all over the entire cell.
Right.
So why not in the oxygen then?
Why not in oxygen?
In titanium oxide, there are oxygen.
Bromine is more aggressive. Not.
Why titanium?
Why here not oxygen? Good question, and the answer does exist. So, if you consider
because the age of the conduction band is originating from titanium, not from oxygen, right?
Yes. So, if you do have only titanium dioxide in your simulation cell, your conduction band is composed of titanium 3D, and valence band is composed of oxygen 2p. So there is, if you do probe current PDOS, there will be no oxygen-related orbitals in the conduction band.
Yeah.
So it was 3 movies, 1 left. I don't know about you, I'm already tired. I need to shorten it substantially. No.
Take a break. We can like next week.
No, next week to UND.
Yeah, everyone comes to UND to listen to you. No?
I can take 3 people in the car, but not everyone. Only maybe a pilot.
Is it 3 including me?
Well, we can put someone in the trunk.
No, you can put someone in the middle, in the back middle.
Okay, 4.
Oh.
So it's methods that probably should be sometimes at the beginning. So second order perturbation in respect to electron-ion interaction. Couplings are going from the non-adiabatic couplings along on the flight trajectory. If one wants, one can make friendship with Professor Krzyzewski and his best group members for excitonic effects. And what is important for radon and for Fatima for the future. If you dope, if you functionalize your perovskite with transition metal doping, with unpaired spins, one needs to have unrestricted DFT, or maybe not DFT, unrestricted Bethe-Salpeter equation. But perovskite itself, even without any magnetic doping, perovskite itself is composed of heavy ions, lead and bromine, and sometimes iodine. and there are relativistic effects and spin-orbit coupling. So the spin is not a good quantum number, and generally one needs to go from just from two components, spin up and spin down. One needs to consider them as not independent set of orbitals, but connected spinors. And then all things, including like potential, all operators start having 4 components, right? So if you do not have spin orbit, it will be only diagonal components. If you allow them to mix, there will be components. And one needs to make appropriate adjustments to the oscillator strength for optical properties and for the non-adiabatic couplings. So there will be also traces of the fact that orbitals are spinors rather than like two component spinors. Okay, and here is an idea of why one would put doping into perovskite quantum dot. So as we already discussed, and everyone in this audience knows, the ability of material to emit does depend on skills of a chemist who cooks your quantum dots, on presence or absence of ligands on the surface. Right? And sometimes ligands may desorb. One can choose wrong ligands, or it can be not ideal surface. So it's expected that quantum dot is emissive, but sometimes there are surface traps. If one would dope the quantum dot with transition metal, which experiences splitting due to crystal field, in this bromine environment, crystal field of, well, I cannot be general, for this specific doping is smaller than a gap of the parent structure. And because of accumulation of several factors, the selection rules become favorable for making transition between these splitted states optically active. And then this optically active state becomes independent of what is going on the surface. So it will become very stable emitter with or without ligands. So you just excite and observe emission. It is an original idea. And you see, orbitals occupied and unoccupied are localized only on the doping atom. Well, if you, here's the structure: the scaffold of the perovskite, the semi-transparent ligands, and this blue cyan spheres are cations of cesium. Without spin orbit, gap will be bigger. With spin orbit, it shrinks by more than half electron volt. And if one includes spin orbit, one would allow originally forbidden transitions with flip of spin. So if you need to restrict yourself by if you are restricted by unrestricted DFT, then your absorption and emission will be absent of the spin flip transition. But you can at least consider the density of excited states corresponding to spin flip transition and show that they are at right energy. And if it is this spin orbit, then this spin forbidden transition come to the redder part of a spectrum, and it is what is expected to give larger photoluminescence. So there was an attempt to do standard practice for non-adiabatic dynamics to go along the trajectory, see how the orbital's energy change in time, how the couplings develop along the trajectory, and then plug it into the standard protocol for electron dynamics and emission. What was potentially dangerous, again, if you are looking at them, originally the doping is set up to be octahedral, but along thermalized molecular dynamics, it prefers to become tetrahedral, so it breaks symmetry inside this structure and prefers to coordinate, to attract 4 out of 6 bromines closer and keep other 2 further apart. So if you do ground state, it may not be observed, but if you do excited state, it can be an issue. Not that we need to panic, but to pay attention. Maybe it's a discovery. And as time passes by, this couplings between states allow the change of the energy of electron hole versus time. As time passes by, electron floats to lower energy and hole floats up to higher energy. In presence of spin orbit, the relaxation in this work by Aaron is found to be slower because spin orbit brings additional splitting, additional subgaps. This result of Aaron is controversial to a recent publication of Alexei Akimov, who claims that presence of spin orbit increases couplings and makes relaxation quicker. So debates are to come. And here is the movie number 4 that was already presented in this audience, but I'm emotionally attached to it and would like to show it once again. So again, orange and electrons and blue are holes, and it is photoexcitation on the undoped perovskite quantum dot slice along the central plane. So as you see, there are some rearrangements of the charge density. It's not ideal. Ideally, most of the density should be only in the center. Here, there are some, I wouldn't say traps, but similar to trap states where more density are on corners right in the center. But the good sign is that amount of density on ligands is vanishing. So indeed, substantial majority, like 99% of the density of both electrons and holes is on the core of the structure, on the perovskite scaffold, and it is expected to be emissive. These cyan portions are cesium. They do not carry any density. Never, they're just spectators for holding the structure, and their densities on leads and bromines. Bromines are here, and leads are on the corners. Well, in this specific set of numerical experiments, the observations were a little against the original expectations. The substantial expectations were put to find noticeable strong emission from doped quantum dot. But it was found that undoped is much brighter. So there is a specific protocol, quite easy to assess quantum yield of photoluminescence. You just make fraction of radiative over radiative plus non-radiative processes. And for undoped, it was about 33%, and for doped, it was less than 1%. This is not what we want to have. And probably the problem is that single determinant DFT is not the best choice for this excitations for transition metal. Or maybe something else is missed. So just plain addition of spin orbit could be insufficient. Maybe inclusion, taking into account excitons, would solve this problem and would make this transition brighter. Maybe are some additional effects. So it is an open problem. But on experiment, this one is brighter than this one. Well, it's on old slide. Now there is much more migration. Well, thank you for your attention. I'm done. Feel free to ask questions. He didn't have enough. Questions 1? Questions 2? Yes?
Just a simple question. So everything you showed was just strict standard PVE, or was something that you showed higher level?
We had some HSC06, but only for analysis of ground state. Maybe I didn't show it, but we do have it. But computation of non-adiabatic couplings with hybrid functionals is too much, yes. There are brave heads in the community who tried it once and made conclusions that now we can use just as a reference. So Alexei Timov did try it about 2-3 years ago to do hybrid functional for non-adiabatic coupling for very small silicon clusters. And if you read it quickly, it sounds like they have effect, but if you read in detail, presence of hybrid functionals substantially affect energy of sets, subgaps.
As we type.
But not the shape of orbitals or couplings. But if one throws everything together, the change of the subgaps noticeably affect the final result. So the if the cost of hybrids is like 2 orders of magnitude higher, one needs to design tricks. And one possible trick is to correct energies based on hybrid, but keep computing couplings based on pure DFT through GGPB. Okay? More questions? Well, if no, thanks much for. Yep. Maybe there will be meeting next Friday here, but I will be absent. Or should we cancel the meeting?
Because
should we cancel or should we?
Why?
You guys, should you have the meeting next Friday? Not
yes,
Tuesday.
so, because we're still waiting for Levi to present his stuff on from Los Lamas, you promised.
Then you need to record it so that.
delay because of this. Huh?
I will. Oh, there will be secrets. You cannot physically record, or you don't have permission to record it.
Technically, I need to get stuff from Los Alamos that I think would take longer than a week, so I would rather not record it.
Okay.
But if both of you are going to be gone, then I'll try and get it that I could record
I
it.
probably will stay.
Oh, okay.
Because I have heard your presentation. Oh, and just to remind those, I guess, you're also TA, right? Then this might be applicable to you as well. Don't forget to finish your safety